Welcome. I am so glad you are here. Tonight, we are going to take a long, quiet journey together. We will leave the noise and the rush of the day behind us. We will drift upward, past the clouds, past the moon, and into the vast, silent ocean of the cosmos. In this story, titled The Terrifying Truth About the Real Scale of Deep Space, we will explore just how enormous our universe really is and how we, tiny as we are, managed to figure it out. This is a place to slow down. There is no hurry here. The storytelling will be gentle and paced to help you unwind, relax your shoulders, and perhaps drift off into a deep, peaceful sleep. We will walk through the history of discovery, from the quiet observatories of Arizona to the frozen edges of the solar system, listening to the silence of the stars. So, find a comfortable position, take a deep breath, and let your mind wander with me into the dark. The night sky looks quiet. When you stand in your backyard and look up at the stars, everything seems still and silent. But for the people who study the sky, the astronomers, the universe is full of action. Today, these scientists can do things that seem like magic. Their tools are so powerful that if someone struck a single wooden match on the surface of the moon, an astronomer on Earth could see the tiny flash of light. They can look at stars that are incredibly far away. Some of these stars are so distant that if we traveled in our fastest spaceship, it would still take us 500,000 years to reach them. Yet, just by watching these stars wobble and throb, astronomers can tell if there are planets orbiting them. They can even guess if those planets might have water or air, or if they are just dead rocks. They use giant radio telescopes to catch invisible signals from space. These signals are very weak. In fact, a famous scientist named Carl Sagan once explained just how weak they are. He said that if you took all the energy collected by all the radio telescopes since 1951, it would be less than the energy of a single snowflake hitting the ground. That is how sensitive these machines are. They are hunting for ghosts in the dark. Because astronomers are so good at finding difficult things, it is very surprising to learn that they missed something very big in our own neighborhood for a long time. For many years, nobody knew that the planet Pluto had a moon. It wasn't until the summer of 1978 that this changed. The discovery happened in a place called Flagstaff, Arizona, at the U.S. Naval Observatory. A young astronomer named James Christie was doing his job, looking at photos of Pluto. These were not the colorful, clear pictures we see on the internet today. In 1978, photos of space were grainy and black and white. Christie was looking at a picture of Pluto, and he noticed something strange. Pluto looked like a fuzzy blob of light, but there was a bump on the side of it. It looked a bit like a snowman that was melting. At first, he might have thought it was just a mistake in the photograph, maybe a piece of dust or a flaw in the camera. But the bump was there. He showed the picture to his colleague, Robert Harrington. They looked at it together. They realized that the bump was not a mistake. It was a moon. It was orbiting Pluto, very close to the planet. This was a huge discovery. It was also a big shock. For a long time, astronomers thought Pluto was much bigger than it actually is. When they looked at Pluto through old telescopes, they saw one big blob of light. They thought all that light came from a single, large planet. But now, Christie had proven that the blob was actually two things: a small planet and a moon right next to it. This meant that Pluto was actually quite tiny. The space that everyone thought was just Pluto was actually shared by the planet and its moon. Suddenly, Pluto lost its status as a big, important planet. It was revealed to be smaller than our own moon. It was smaller even than the planet Mercury. In fact, there are 7 moons in our solar system that are bigger than the planet Pluto. You might ask a simple question. Why did it take so long to find a moon in our own solar system? If astronomers can see a match on the moon, why couldn't they see a giant rock orbiting Pluto? The answer is a little complicated. Partly, it is because of where astronomers choose to look. We often imagine that astronomers spend every night scanning the whole sky, like a security guard watching a bank of monitors. But that is not true. Most telescopes are designed to look at very, very tiny pieces of the sky. They focus on deep space to look for black holes or distant galaxies. It is like looking at the world through a thin drinking straw. You can see great detail in that one tiny circle, but you miss everything else around it. There are very few telescopes that just scan the whole sky to see what is there. Most of the ones that do that belong to the military, not to scientists. Also, we have been spoiled by artists. When we see pictures of space in magazines or on TV, they are beautiful. The planets are sharp and colorful. We see Pluto as a crisp, icy ball with a bright moon behind it. But that is not what astronomers see. In 1978, Pluto was just a piece of cosmic lint. It was a faint, fuzzy dot. The moon was just an extra bit of fuzziness on the side. It was so hard to see that after Christie found it, it took another 7 years before anyone else could find it again to prove he was right. It is nice that this discovery happened in Flagstaff, Arizona. Flagstaff is a special place for Pluto. It is the town where Pluto was discovered in the first place, back in 1930. The story of Pluto really begins with a man named Percival Lowell. He was from a very old and very rich family in Boston. There was even a famous rhyme about his family, saying that the Lowells only spoke to the Cabots, and the Cabots only spoke to God. That is how fancy they were. Percival Lowell used his money to build the Lowell Observatory in Flagstaff. He loved astronomy, but he had some strange ideas. He is most famous for believing that the planet Mars was covered in canals. He thought that intelligent Martians had built these giant waterways to carry water from the icy poles of Mars to the dry land near the equator to grow their crops. He wrote books about it and convinced many people that there was a civilization on Mars. Of course, we know now that this wasn't true. Mars is a dry, cold desert. But Lowell had another big idea. He was convinced that there was a 9th planet hidden in the darkness beyond Neptune. He called it Planet X. Lowell believed Planet X existed because of math. He looked at the orbits of the planets Uranus and Neptune. They didn't move exactly the way they were supposed to. Lowell thought that a giant, invisible planet was out there, using its gravity to pull on them. He spent the last years of his life hunting for this gas giant. Sadly, the search exhausted him. He died suddenly in 1916, without ever finding his Planet X. After he died, the search stopped for a long time. His family fought over his money and his estate, and the telescope sat quiet. But in 1929, the directors of the observatory decided to try again. By this time, The stories about the Martian canals had become a bit of a joke. The observatory needed a new success to make people respect them again. They decided to hire someone new to look for Planet X. They didn't hire a famous scientist from a big university. They hired a 22-year-old farm boy from Kansas named Clyde Tombaugh. Clyde Tombaugh had no formal training in astronomy. He didn't have university degrees, but he was smart and he was incredibly patient. He was used to hard work on the farm. He built his own telescopes from scratch using old farm machinery parts. He sent drawings of Jupiter and Mars to the Lowell Observatory, and they were so impressed that they gave him the job. His job was very difficult and very boring. He had to take pictures of the sky at night. Then, he used a machine called a blink comparator. This machine allowed him to look at two photos of the same piece of sky taken on different nights. He would flip back and forth between the two images. Click, clack, click, clack. If a star was a real star, it would stay in the same place in both photos. But if one of the dots was a planet, it would move slightly between the first night and the second night. Tombaugh had to stare at thousands and thousands of stars, looking for one tiny dot that jumped. He did this for a year. It was tiring work, but Clyde Tombaugh was diligent. Then, on a February afternoon in 1930, he saw it. He was looking at photos taken in January. In one part of the sky, a faint point of light had shifted. He checked it again. It moved. It wasn't a star. It was a planet. It was a miraculous find. What makes it even more amazing is that Percival Lowell was wrong. The math that predicted Planet X was full of errors. There was no giant gas planet pulling on Neptune. The irregularities in the orbits didn't really exist. Tombaugh had found Pluto by pure luck and hard work. Tombaugh realized immediately that this new world was not the giant monster Lowell had predicted. The dot of light was tiny and faint. It wasn't a gas giant. It was just a little icy speck. But the world was ready for good news. In 1930, people were excited by discovery. It didn't matter that the planet was small. It was the first planet discovered by an American. Newspapers went wild. People all over the world celebrated. They needed a name for the new world. An 11-year-old girl in England suggested the name Pluto, after the Roman god of the underworld, because the planet was so far away and dark. The astronomers liked it for another reason too. The first two letters of Pluto, P and L, were the initials of Percival Lowell. It was a perfect tribute to the man who started the search. So, Percival Lowell was hailed as a genius, even though his math was wrong. Poor Clyde Tombaugh, the farm boy who actually did the work, was mostly forgotten by the public. But among astronomers, Tombaugh is still a hero. He proved that if you look hard enough at the dark sky, you can find things that everyone else has missed. Even today, the mystery of Planet X continues. Some astronomers still think there might be something else out there. They think there could be a real whopper of a planet, maybe 10 times the size of Jupiter, hiding very far away. It would be so far out that the sun would look like just a bright star. This planet would be invisible to us, because there is no sunlight for it to reflect. If this giant planet exists, it wouldn't be like the rocky Earth, or even like gassy Jupiter. It would be almost like a failed star. Some scientists point out that most stars in the universe have a partner. They are binary systems with two suns orbiting each other. Our sun is a bit odd because it is all alone. Perhaps this dark, distant planet X is the brother our sun never quite had. But let us return to Pluto. Even after finding it, nobody was quite sure what it was. We didn't know how big it was or what it was made of. We didn't know if it had an atmosphere like Earth or if it was just a dead stone. For a long time, it was just a question mark at the edge of the map. Many astronomers today believe that Pluto is not really a planet at all. They think it is just the largest object in a giant ring of garbage called the Kuiper Belt. The Kuiper Belt is a fascinating and messy place. It was first theorized in 1930 by a man named F.C. Leonard right after Pluto was found. Later, a Dutch astronomer named Gerard Kuiper expanded on the idea, so it was named after him. The Kuiper Belt is like a junkyard for the solar system. It is filled with icy rocks and debris left over from when the planets were formed. This belt is where many comets come from. You have probably heard of Halley's Comet, which flies past Earth once every 76 years. It comes from the Kuiper Belt. These are called short-period comets because they visit us fairly often. There are other comets, the long-period comets, that take thousands of years to return. They come from a place even farther away called the Oort cloud, but we will get to that later. Pluto fits in very well with the objects in the Kuiper Belt. It doesn't act like the other planets. It is a rebel. Most planets in our solar system are very well behaved. They orbit the sun on a flat path, like race cars driving around a level track. If you put all the planets on a table, they would all roll along the surface of the table together. But Pluto is different. First, its path is tipped. Imagine someone wearing a hat, and then they tilt the hat to the side to look cool. That is what Pluto's orbit looks like. It is tilted at an angle of 17 degrees compared to all the other planets. It does not sit flat on the table. It dives below the table and then soars high above it. Because its path is so strange and oval-shaped, Pluto does something else that no other planet does. It crosses the lane of its neighbor. Think of the solar system like a running track with lanes. Mercury is in the inside lane, then Venus, then Earth, and so on, all the way out to Neptune. Usually, planets stay in their own lanes. But Pluto's orbit is so stretched out that for long periods of time, it actually cuts inside Neptune's orbit. It gets closer to the Sun than Neptune is. This means that for about 20 years of its long year, Pluto is not the farthest planet from the Sun. Neptune is. This actually happened very recently. From 1979 until February 1999, Neptune was the most distant planet in the solar system, and Pluto was second to last. It was only on February 11, 1990, that Pluto moved back into the outside lane. It will stay there now for the next 228 years before it cuts inside again. So, if we insist on calling Pluto a planet, we have to admit it is a very odd one. It is incredibly small. It has only 1/4% of the mass of the Earth. That is a tiny fraction. To give you a better picture of how small it is, imagine picking Pluto up and placing it on top of the map of the United States. It would not even cover the whole country. It would cover less than half of the lower 48 states. This small size makes Pluto a complete anomaly. Before we really understood Pluto, we thought the solar system was organized very neatly. We had 4 rocky planets close to the Sun: Mercury, Venus, Earth, and Mars. Then we had 4 giant balls of gas: Jupiter, Saturn, Uranus, and Neptune. It was a perfect pattern. But then, at the very end, we have this tiny, solitary ball of ice. It doesn't fit the pattern at all. This is why many astronomers think Pluto is just the first of a new class of objects. They believe that if we look hard enough, we will find many more icy spheres in that same dark corner of space. In fact, we have already started finding them. After James Christie found Pluto's moon in 1978, other astronomers began to look at that section of the sky with much more focus. They realized they had been ignoring the background. By December 2002, they had found over 600 additional objects out there beyond Neptune. They call these trans-Neptunian objects, or sometimes they use a cuter name, Plutinos. Some of these new objects are quite big. One of them is named Varuna, and it is nearly as large as Pluto's moon. Astronomers now guess that there could be billions of these objects floating in the dark. The problem with finding them is not just that they are small or that they are far away. The problem is that they are dark. Very, very dark. In astronomy, we talk about something called albedo. Albedo is just a fancy word for reflectiveness. It measures how much light bounces off an object. A mirror has very high albedo. A black t-shirt has low albedo. There's another Roman of voice. These icy rocks out past Pluto have an albedo of just 4%. That is about the same reflectiveness as a lump of charcoal. Now, imagine taking a lump of charcoal and throwing it into a dark room 4 billion miles away. Then try to find it using a telescope. That is the challenge astronomers face. These objects are black lumps floating in a black sky. It is amazing we have found any of them at all. To really understand why this is so difficult, we need to understand the distances involved. We need to understand how big space actually is. The word space is very appropriate because there is so much of it. It is almost entirely empty. The distances between things are so vast that our human brains struggle to comprehend them. We hear numbers like billions of miles, but they don't mean much to us because we have nothing to compare them to. So, let us try a mental experiment. Let us imagine, just for fun and education, that we are going to go on a trip. We are going to pack our bags and get into a rocket ship. We aren't going to go to the stars or other galaxies. That is too far. We are just going to travel to the edge of our own solar system. We want to see how big our local neighborhood really is. I have to warn you though, we won't be home for dinner. First, let's talk about speed. In science fiction movies, spaceships can zip across the galaxy in a few hours. In reality, the speed limit of the universe is the speed of light. Light travels incredibly fast, minus 186,000 miles every single second. If we could travel at the speed of light, we could get to Pluto in about 7 hours. That sounds like a manageable trip, perhaps like flying from New York to London. But we cannot travel at the speed of light. We are made of matter. and matter is heavy and slow. We have to travel at the speed of spaceships. Compared to light, spaceships are like slow, lumbering turtles. The fastest speed any human-made object has ever achieved belongs to the Voyager 1 and Voyager 2 spacecraft. These probes were launched back in the 1970s and are now flying away from us at about 35,000 miles an hour. 35,000 miles an hour sounds incredibly fast. It is much faster than a bullet. If you could drive your car that fast, you could cross the United States in about 4 minutes. But in the vast ocean of space, that speed is barely a crawl. The Voyager spacecraft are special. They were launched in August and September of 1977 for a very specific reason. At that time, the giant planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, were lined up in a special way. This alignment only happens once every 175 years. It was a rare opportunity. Because the planets were lined up, the Voyager spacecraft could use a trick called a gravity assist. It is a bit like a cosmic game of crack the whip. The spacecraft would fly close to Jupiter, and Jupiter's massive gravity would grab it and fling it toward Saturn. Then Saturn would fling it toward Uranus, and so on. Each time the spacecraft swung round a planet, it picked up more speed. Even with this perfect alignment and the extra speed from the gravity assists, it took the Voyager spacecraft a long time to get anywhere. It took 9 years just to reach Uranus. It took 12 years to cross the orbit of Pluto. So, if we want to go to Pluto in our imaginary rocket and we travel at the best speeds humans have ever achieved, we have to be prepared for a decade of travel just to get there. NASA is planning a mission called New Horizons that is scheduled to launch in January 2006. It will use better technology and the gravity of Jupiter to try to get to Pluto in about 10 years, but getting home again would take even longer. It is going to be a very long trip. As we fly out into the dark on our imaginary journey, the first thing we notice is how boring space is. It is remarkably uneventful. We call it the solar system, which makes it sound like a busy machine with lots of moving parts. And it is true that our system has the sun, the planets, their moons, and billions of asteroids and comets. But all of that stuff, the solid objects, takes up almost no room at all. If you gathered every single planet, moon, asteroid, and rock and put them in a pile, they would fill less than 1/1,000,000,000th of the available space. The rest is just nothing. You also realize very quickly that your school teachers lied to you. Think about the maps of the solar system you saw in your classroom. They usually show the sun on one side and then the planets lined up in a row: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. In the pictures, the planets look like neighbors. They look like they are spaced out evenly. Sometimes the artists even draw the outer planets so close together that they cast shadows on each other. This is a necessary lie. If the artists drew the solar system to scale, they wouldn't be able to fit it on a piece of paper. In reality, the spacing is not even. As you move away from the sun, the gaps between the planets get bigger and bigger. Neptune is not just a little bit farther out than Jupiter. It is way, way out there. Neptune is 5 times farther from Jupiter than Jupiter is from us. It is so far away that it receives only 3% as much sunlight as Jupiter does. The distances are so huge that it is basically impossible to draw a scale map of the solar system. Even if you had a textbook with fold-out pages, it wouldn't be enough. Even if you used a roll of poster paper that stretched across the entire classroom, you wouldn't come close. Let's try to build a scale model in our heads to see why. Imagine we shrink the Earth down until it is the size of a pea. Now, let's place this pea on the floor. On this scale, Jupiter, the biggest planet, would be over 1,000 feet away. That is 3 football fields away from our pea-sized Earth. And Pluto? On this same scale, Pluto would be 1.5 miles away. And remember, Pluto is tiny. On this scale, Pluto would be the size of a microscopic bacteria. So, even if you walked 1.5 miles to find it, you wouldn't be able to see it with your eyes. Now, consider the nearest star, Proxima Centauri. On this same scale, where Earth is a pea, Proxima Centauri would not be in the next town, or even the next state. It would be almost 10,000 miles away. You would have to travel halfway around the real world just to reach the next pea in the model. This is why diagrams in books are always wrong. If you shrank the solar system down so that the orbit of Pluto was the size of a frisbee, the planets inside it would be too small to see even with a microscope. If you shrank it down so that Jupiter was the size of the period at the end of this sentence, and Pluto was no bigger than a molecule, Pluto would still be over 35 feet away from Jupiter. So, the solar system is really, really enormous. And as we travel on our rocket ship, moving past the orbit of Mars and into the darkness, the sun begins to shrink. Back on Earth, the sun is a big, warm yellow ball that tans our skin and gives life to our plants. But out here, near Pluto, the sun has become tiny. It has shrunk to the size of a pinhead. It is no longer a big, warm disk. It is just a very bright star in a sea of darkness. In this lonely void, it is easy to understand why we missed things for so long. It is easy to see how a moon orbiting Pluto could remain hidden. It is easy to see how we could miss entire planets if they are dark enough. Until the Voyager spaceships flew past Neptune, we thought Neptune had 2 moons. Voyager found 6 more. When I was a boy, scientists said the entire solar system had 30 moons. Today, the count is at least 90. We have found 1/3 of those in just the last 10 years. The important lesson here is humility. When we talk about the universe, we have to admit that we don't even know everything that is in our own backyard. However, there is another surprise waiting for us on our journey. We have been flying for years. We have passed the orbit of Pluto. We might think that we have reached the finish line. We might think we have reached the edge of the solar system. But if you check your map, you will see that we are not even close. We are currently flying past Pluto in our imaginary rocket ship. We might feel like we have accomplished something huge. We have traveled billions of miles. We have left the planets behind. But the truth is, if we are trying to reach the true edge of the solar system, we have barely left the front porch. Pluto may be the last planet marked on the maps in your school classroom. But the solar system does not end there. In fact, it isn't even close to ending. Before we can say we have truly left the solar system, we have to pass through something called the Oort cloud. The Oort cloud is a massive, drifting kingdom of ice and comets. It surrounds our solar system like a giant spherical shell. But here is the bad news for our journey. We won't reach the Oort cloud for another 10,000 years. That is correct. 10,000 years. Pluto is not the boundary line. If the journey from Earth to the edge of the solar system was a 50,000-mile highway, Pluto would be at mile marker 1. It is barely 1/50,000th of the way to the end. That is how vast our solar system truly is. The maps that show Pluto as the end are misleading because they simply run out of paper. In reality, there is absolutely no chance that we will ever make this trip. A trip of 240,000 miles to the moon is still a massive challenge for the human race. We have not been back there in decades. There was a moment, years ago, when the first President Bush suggested a manned mission to Mars. It sounded exciting, but then someone sat down and did the math. They calculated that it would cost $450 billion. Even worse, they realized that the crew would almost certainly die. Space is full of high-energy solar particles, invisible radiation that tears through DNA like bullets. On a long trip to Mars, without the protection of Earth's atmosphere, the astronauts would be exposed to deadly amounts of this radiation. We simply do not have the shields to protect them. So, the idea was quietly dropped. Based on everything we know today and everything we can imagine for the future, no human being will ever visit the edge of our own solar system. It is just too far. It is physically impossible for us. In fact, the Oort cloud is so far away that we can't even see it. Even with our best machine, the Hubble Space Telescope, we cannot see into the cloud. We don't actually know for a fact that it is there. We can't take a picture of it. Its existence is entirely hypothetical. Astronomers are sure it exists because the math says it must be there, and because we see comets coming from that direction, but we have never seen the cloud itself. The only thing we can say with confidence is that the Oort cloud starts somewhere far beyond Pluto and stretches out into the cosmos for about 2 light years. To understand these distances, astronomers use a ruler called the astronomical unit, or AU. 1 AU is the distance from the Sun to the Earth. Pluto is about 40 AUs away from us, but the heart of the Oort cloud is about 50,000 AUs away. In a word, it is remote. But since this is an imaginary journey, let's pretend we have magical shields and infinite fuel. Let's pretend we have traveled for 10,000 years and have finally arrived in the Oort cloud. The first thing you might notice is how peaceful it is. It is incredibly quiet. We are so far from home now that the sun is just a tiny, bright star in the distance. It is not even the brightest star in the sky anymore. It is amazing to think that the sun, which is now just a tiny twinkle, still has enough gravity to hold on to these comets. It reaches out across trillions of miles to keep them on a leash. However, the bond is very weak. Because the gravity is so faint out here, the comets don't zoom around like planets. They drift in a slow, stately manner. They move at only about 220 miles an hour. These comets are like lonely ghosts floating in the dark. From time to time, something disturbs them. Maybe a passing star gets a little too close, and its gravity gives them a gentle nudge. This slight push changes their path. Sometimes a comet gets nudged outward into the empty void of the universe and is never seen again. But sometimes they are nudged inward. They begin a long, slow fall toward the sun. About 3 or 4 times a year, one of these long-period comets passes through the inner solar system where we live. These are the visitors from the deep dark. Just occasionally, one of these stray visitors hits something solid. Sometimes they hit Earth. That is actually why we have come all this way in our story. We are here to watch a specific comet. Right now, in the quiet dark of the Oort cloud, a comet has just been nudged. It has begun a long fall toward the center of the solar system. It has a specific destination, though it doesn't know it yet. It is headed for a place called Manson, Iowa. It is going to take a very long time to get there, at least 3 or 4 million years. So, we will leave it alone for now. We will let it fall silently through the dark, and we will come back to it much later in our story. So, that is your solar system. It is big, mostly empty, and surrounded by a cloud of ice. But what is beyond that? What lies outside the solar system? Well, the answer is both nothing and a great deal, depending on how you look at it. In the short term, the answer is nothing. The space between stars is emptier than anything we can create on Earth. The most perfect vacuum scientists can make in a laboratory still has more stuff in it than the emptiness of interstellar space. There is a whole lot of this nothingness before you get to the next something. Our nearest neighbor in the galaxy is a star called Proxima Centauri. It is part of a group of 3 stars known as Alpha Centauri. It is about 4.3 light-years away. In the terms of the galaxy, this is a very short distance. It is a hop, skip, and a jump, but for us, it is a nightmare of distance. 4.3 light-years is about 100 million times farther than a trip to the moon. If we tried to go there in our spaceship, it would take at least 25,000 years to arrive. And even if you made that trip, if you spent 25,000 years flying through the dark, you wouldn't really be anywhere. You would just be at a lonely group of stars in the middle of a vast nowhere. If you wanted to keep going to the next important landmark, a star called Sirius, you would have to travel another 4.6 light-years. And so it would go. You would have to hop from star to star across distances that are impossible to comprehend. If you tried to reach the center of our own galaxy, the trip would take longer than humans have existed as a species. Let me repeat, space is enormous. The average distance between stars out there is 20 million miles. Even if you could travel near the speed of light, these distances are incredibly challenging. This brings us to a popular topic: aliens. People love to tell stories about aliens visiting Earth. They talk about flying saucers landing in fields in England to flatten the crops into circles. They talk about aliens kidnapping people on lonely roads in Arizona to perform experiments. But when you look at the distances involved, these stories seem very unlikely. Why would alien beings travel billions and billions of miles just to scare a guy in a pickup truck? It is possible, of course. Maybe aliens have teenagers who like to play pranks, but the effort required to cross those distances makes it seem like a lot of work for a small joke. However, just because they probably aren't visiting us doesn't mean they aren't out there. Statistically, the chances that there are other thinking beings in the universe are actually quite good. Nobody knows exactly how many stars are in our galaxy, the Milky Way. Estimates range from 100 billion to perhaps 400 billion stars. And remember, the Milky Way is just one galaxy. There are about 140 billion other galaxies in the universe, and many of them are even bigger than ours. In the 1960s, a professor at Cornell University named Frank Drake got excited by these huge numbers. He wanted to figure out how likely it was that we are not alone. So, he created a famous formula called the Drake equation. The equation is designed to calculate the number of advanced civilizations in the galaxy. It works like a funnel of probabilities. You start with the total number of stars in the galaxy. Then, you divide that by the number of stars that are likely to have planets orbiting them. Then, you take that number and divide it by the number of planets that are in the right spot to support life. Not too hot, not too cold. Then, you divide that by the number of planets where life actually begins. Then, you divide by the number where life becomes intelligent. And so on. At each step, the number gets smaller and smaller. It shrinks colossally. But here is the amazing thing. Because you start with such a massive number of stars, billions and billions, even after you divide it and divide it again, you still end up with a big number. Even with the most conservative guesses, the Drake equation suggests that there should be millions of advanced civilizations just in the Milky Way galaxy alone. That is a very exciting thought. We might be one of millions of intelligent species. But then, reality comes crashing back in. The problem, once again, is distance. Space is so spacious that the average distance between any two of these civilizations is calculated to be at least 200 light-years. 200 light-years doesn't sound like much when you just say the words. But think about what it means. It means that light takes 200 years to travel from them to us. If there are aliens on a planet 200 light-years away, and they are looking at Earth through a super powerful telescope right now, they are not seeing you and me. They are not seeing cars or airplanes or the internet. They are seeing the light that left Earth 200 years ago. They are watching the French Revolution. They are seeing Thomas Jefferson. They are looking at people in powdered wigs and silk stockings. They are watching a world where people don't know what an atom is. They are watching people who think electricity is a magic trick you do by rubbing a piece of amber with fur. If these aliens sent us a radio message to say hello, it would take 200 years to get here. If they sent it when they saw Thomas Jefferson, we would just be getting it now. And the message would probably say, "Nice wigs," or "Congratulations on your whale oil lamps." By the time we replied and said, "Actually, we have iPhones now," another 200 years would pass before they heard us. So, the distance makes communication almost impossible. 200 light-years is a gap so big that it separates us completely. Even if we are not technically alone in the universe, in all practical terms, we are alone. We are isolated by the sheer size of the dark. Carl Sagan, the famous astronomer, once calculated the number of probable planets in the entire universe. He came up with the number 10 billion trillion. That is a 1 followed by a lot of zeros. It is a number beyond imagining. But he also reminded us that those planets are scattered through a space that is even more beyond imagining. He wrote, "If we were randomly inserted into the universe, the chances that you would be on or near a planet would be less than 1 in a billion trillion trillion. To put that in perspective, imagine the universe is a giant ocean. A planet is like a single atom of water in that ocean. Worlds are incredibly rare. They are precious. This is why it was actually quite nice when, in February 1999, the International Astronomical Union decided to officially classify Pluto as a planet. This was before they changed their minds again later. The universe is such a big, cold, lonely place. We need all the neighbors we can get. So, we have established that space is big. But how do we know all of this? How do we know how big the Earth is? Or how far away the Sun is? Or what makes a star burn? Today, we take these facts for granted. We learn them in school. But for most of human history, we didn't know any of this. People had to figure it out. And the story of how they figured it out is full of mistakes, arguments, and some very colorful characters. To understand how we measured the universe, we have to go back to the beginning. We have to go back to a time when people were trying to measure the Earth itself. In the 18th century, scientists in France decided that they needed to know the exact shape of the Earth. By this time, educated people knew the Earth was round. They had known that for a long time, but they didn't know if it was a perfect sphere, like a marble, or if it was shaped differently. This was not just a question for map makers. It was a matter of national pride and scientific theory. There were two main teams with different ideas. On one side there were the English, led by the ideas of Isaac Newton. Newton had said that because the Earth spins rapidly, the centrifugal force should push the equator outward. He believed the Earth was an oblate spheroid. This means it is flattened at the top and bottom and bulges in the middle, like a pumpkin or a ball of dough that someone is spinning on a table. On the other side were the French astronomers, specifically a family named Cassini. They believed that the Earth was a prolate spheroid. This means it was stretched out at the poles and skinny in the middle, like an American football standing on its tip, or a melon. So, the question was simple. Is the Earth fat or is it tall? To settle the argument, the Royal Academy of Sciences in Paris decided to organize a grand experiment. They would send two teams of scientists to opposite ends of the Earth. One team would go north, to the icy lands of Lapland near the Arctic Circle. The other team would go south, to the equator in Peru. Their job was to measure the length of 1 degree of latitude on the Earth's surface. If Newton was right, and the Earth bulged at the equator, the degree would be longer in the north and shorter at the equator. If the Cassinis were right, it would be the other way around. The mission to the north went smoothly. The team, led by a man named Pierre Maupertuis, went to Scandinavia, endured the cold, took their measurements, and came home in about 18 months. They did a good job. The mission to South America, however, was a disaster from start to finish. It is one of the most famous stories of scientific misfortune in history. The expedition was led by 3 men, Louis Godin, Pierre Bouguer, and Charles-Marie de la Condamine. They were all very smart, but they were terrible at working together. They started hating each other almost as soon as the ship left France in 1735. When they arrived in South America, everything went wrong. They had to travel across wild mountains and through dangerous jungles. They were not prepared for the terrain. The Andes Mountains are huge and rugged. To measure the distance, they had to use a method called triangulation. Triangulation works like this. You measure a straight line on the ground very, very accurately. This is your baseline. Then you pick a point in the distance, like a mountain peak. You look at that peak from both ends of your baseline and measure the angles. If you know the length of the base and the two angles, you can use math, trigonometry, to calculate the distance to the mountain without actually walking there. Then, you use that new line to measure the next mountain and the next, forming a chain of triangles across the country. It sounds simple on paper. In the Andes, it was a nightmare. They had to climb steep peaks, often in blinding snowstorms, to set up their sighting markers. They had to wait for weeks for the fog to clear so they could see the next mountain. They suffered from altitude sickness. They were attacked by bugs. Their equipment broke. But the biggest problem was their personalities. La Condamine was a wealthy, charming man who loved to explore and talk to people. Bouguer was a serious, grumpy scientist who just wanted to do the work. They annoyed each other so much that they eventually stopped speaking. For the last few years of the trip, they would only communicate by writing notes to each other, even though they were living in the same camps. The third leader, Godin, wasn't much help either. He spent a lot of money on a diamond for his mistress, and mostly did his own thing. The expedition was supposed to take a few years. It took them 10 years. While they were stuck in the jungle arguing and fighting off fevers, the northern team had already returned to Paris. The northern team announced their results. The Earth was flattened at the poles. Newton was right. The French theory was wrong. The Earth is shaped like a pumpkin, not a melon. When the South American team finally dragged themselves back to France, they found out that everyone already knew the answer. They had spent a decade of suffering for almost nothing. Bouguer and La Condamine were so bitter that they refused to be in the same room. However, despite the drama, they did bring back something valuable. They had proven the size of the Earth with much better accuracy than ever before. This was the first step in understanding the scale of the universe. Once we knew the size of the Earth, we could try to measure the distance to other things. The next big challenge was to measure the distance from the Earth to the Sun. This distance is called the astronomical unit, AU. As we mentioned in earlier parts, it is the basic ruler for the solar system. Today we know it is about 93 million miles. But in the 18th century, nobody knew for sure. Some people thought it was 4 million miles, others thought it was much more. It was like trying to draw a map without knowing how long a mile is. To fix this, astronomers came up with a brilliant plan involving the planet Venus. Venus orbits the Sun closer than we do. Very rarely, Venus passes directly between the Earth and the Sun. When this happens, you can see a tiny black dot, Venus, moving across the bright face of the Sun. This is called a transit of Venus. A famous British astronomer named Edmund Halley, the same man who discovered Halley's comet, realized that this transit could be used to measure the solar system. The idea relied on a simple effect called parallax. You can see parallax right now. Hold your finger up in front of your face. Close one eye, then open it and close the other. Your finger seems to jump side to side compared to the background. That jump is parallax. Halley figured out that if two astronomers stood at different places on Earth, one far in the north and one far in the south, and watched Venus cross the Sun, they would see it cross at slightly different places. It's just like the finger jumping. If they timed exactly how long the crossing took, they could use the difference in time to calculate the distance to Venus, and then use math to find the distance to the Sun. There was just one problem. Transits of Venus are incredibly rare. They happen in pairs, 8 years apart, but then you have to wait over 100 years for the next pair. Halley predicted there would be a transit in 1761 and another in 1769. He knew he would be dead by then, but he left strict instructions for the next generation of astronomers. Do not miss this chance. So, when 1761 approached, the scientific world got ready. This was going to be the biggest international scientific project in history. Nations that were usually at war agreed to let astronomers pass through their borders safely. Ships were packed with telescopes and clocks. Men were sent to Siberia, to Africa, to India, and to America. Unfortunately, the 1761 transit was a disappointment. The weather was bad in many places. Also, astronomers ran into a strange problem called the black drop effect. When Venus moves onto the Sun, it doesn't look like a crisp, round circle. Just as it touches the edge of the Sun, it seems to smear, like a drop of ink touching wet paper. This made it very hard to say exactly when the transit started and ended. The timing was off. The results were messy. So, everyone looked toward the second chance, the transit of 1769. If they missed this one, they would have to wait until 1874. There would be no second chances for anyone alive. This brings us to the story of Guillaume Le Gentil. Le Gentil was a French astronomer. Monsieur Bondeau, Virginia Lest. His story is so sad, it is almost funny. He is probably the unluckiest astronomer who ever lived. He set out from France in 1760 to observe the first transit, the 1761 one. His destination was Pondicherry, a French colony in India. It was a long, dangerous sea voyage. He traveled for months. But just as he was getting close to India, he ran into trouble. France and England were fighting a war, the 7 Years' War, and it turned out that the English had captured Pondicherry. His ship couldn't land. They had to turn around and sail out to sea to avoid being captured. While he was stuck on a rocking ship in the middle of the Indian Ocean, the day of the transit arrived. The sky was clear. He could see the sun perfectly. But because the ship was rolling on the waves, he couldn't keep his telescope steady. He couldn't take any accurate measurements. He had traveled halfway around the world and missed it. This was frustrating, but Le Gentil was a dedicated scientist. He knew the next transit was in 8 years, in 1769. He decided that instead of risking the long trip back to France and then coming all the way back, he would just stay in Asia and wait. He spent the next 8 years traveling around the Indian Ocean. He mapped the coast of Madagascar. He studied the tides. He learned about the local geography. He prepared everything perfectly for the big day in 1769. When the time came, he decided to set up his observatory in Manila, in the Philippines. But then he heard that the Spanish authorities there were suspicious of him. So he changed his mind and went back to Pondicherry, which had been given back to the French by then. He arrived in plenty of time. He built a first-class observatory. He tested his instruments. The weather in Pondicherry was known to be excellent. For the entire month leading up to the transit, the skies were perfectly clear, not a single cloud. Le Gentil was ready. The morning of the transit arrived, June 4th, 1769. He woke up and looked out the window. To his horror, he saw something he hadn't seen in weeks. Clouds. A storm system had moved in overnight. The sky was covered in a thick grey blanket. Le Gentil stood by his telescope and watched helplessly. He could not see the sun. He could not see Venus. He missed the entire thing. 2 hours after the transit finished, the clouds cleared and the sun shone brightly for the rest of the day. Le Gentil was devastated. He had spent nearly 10 years away from home for this one moment, and a random cloud had ruined it. He almost went insane with grief, but his bad luck wasn't over. He packed up his things and caught a ship back to France. He just wanted to go home. However, the trip back was a nightmare. He caught dysentery and nearly died. Then his ship was hit by a hurricane and wrecked off the coast of Africa. He had to wait for another ship. He was stuck in random ports for months. Finally, after being away for 11 years and having absolutely nothing to show for it, he arrived back in France. He walked up to the door of the Royal Academy of Sciences, ready to tell his sad story. But when he got there, the clerk looked at him with confusion. "I am Guillaume le Gentil," he said. "Impossible," they told him. "Le Gentil is dead." It turned out that because he had been gone for so long and had stopped writing letters, everyone assumed he had died years ago. His wife had remarried, his relatives had declared him legally dead, and had divided up his estate and spent his money. He had lost his job at the academy. He was a man with no discovery, no wife, no money, and officially no life. Eventually, he managed to sue his relatives and get some of his life back, but he never did measure the solar system. Fortunately, other people had better luck. An English captain named James Cook, who we know as the man who mapped Australia, was sent to Tahiti to watch the 1769 transit. He had perfect weather. He set up his equipment on a sandy beach, at a place still called Point Venus today, and got excellent data. Astronomers in other parts of the world also got good readings. When they combined all the data, a French mathematician named Jérôme Lalande crunched the numbers. He calculated that the distance from the Earth to the Sun was a little over 93 million miles. He was incredibly close. His number was only off by about 2% from what we know today. Finally, humans had a ruler. We knew how big the solar system was, and once we knew the distance to the Sun, we could start to guess the distance to the stars. But measuring the stars required a whole new leap in imagination. The stars are so far away that the method of triangulation doesn't really work. The angles are too small. To understand the stars, we would need to understand what they are made of. And to do that, we would need to understand the very small things, atoms. This brings us to a man named John Dalton. John Dalton was a modest Quaker teacher who lived in Manchester, England, in the early 1800s. He was a quiet man who dressed in simple clothes and walked softly, but he had a mind that saw the world in a way no one else did. Dalton was interested in everything, but he was especially fascinated by the weather. He kept a diary of the weather every single day for 57 years. He recorded the temperature, the wind, and the rainfall. He recorded over 200,000 observations, but his most important work wasn't about rain. It was about what the rain and everything else was made of. Dalton was the first person to offer a convincing scientific argument for the existence of atoms. The idea of the atom had been around for a long time. The ancient Greeks had talked about it. They wondered what would happen if you took a piece of gold and cut it in half, and then cut that half in half, and kept going forever. Eventually, they guessed, you would reach a tiny piece that could not be cut anymore. They called this atamos, which means uncuttable. But for 2,000 years, this was just a guess. It was philosophy, not science. Nobody could prove it. Most people thought that matter was continuous, like Play-Doh. They thought you could keep dividing it forever, and it would just get smaller and smushier. John Dalton was the man who changed this. In 1808, he published a book with a very boring title, A New System of Chemical Philosophy. But inside, the ideas were explosive. Dalton proposed that everything in the world is made of tiny, indestructible particles called atoms. He said that these atoms are like little billiard balls. He believed that all atoms of a specific element, like hydrogen or copper, are identical, and he said that you cannot create or destroy them. You can only rearrange them. Think of it like Lego bricks. You can build a castle, then take it apart and build a boat, then take it apart and build a spaceship. The shape of the toy changes, but the bricks themselves stay exactly the same. That is how the universe works. Chemical reactions are just atoms swapping partners to build new things. Dalton was a strange man. He was a Quaker, which meant he lived a very simple life. He wore plain clothes and spoke very directly. He was also colorblind. He did so, how friendly. He did faithful and passionate intimate faith. In fact, he was the first person to study colorblindness scientifically. For a long time in England, the condition was actually called Daltonism. He was so curious about his own eyes that he left instructions for his doctor to cut them open after he died to see what was wrong with them. The doctor did, and found that Dalton's eyes were perfectly normal. The problem was in his brain, or rather, in the way his eyes processed light, which was a mystery at the time. That despite his simple life, Dalton gave us the modern world. He gave us the understanding that the world is built of pieces. However, accepting atoms is one thing. Understanding how small they are is another thing entirely. Atoms are small. They are so small that it is hard to find words to describe them. Imagine a single millimeter. That is the tiniest line on a ruler. Now, imagine a line of atoms stretching across that millimeter. You would need 10 million of them lined up shoulder to shoulder to fill that tiny space. Or think of it this way. If you wanted to hide behind a human hair, you would have to pile up 500,000 atoms just to equal the width of that single hair. They are so small that a single drop of water contains more atoms than there are stars in the entire visible universe. It is a number so big that your calculator cannot even show it. Because they are so small and tough, atoms last practically forever. They are incredibly durable. The atoms that are inside you right now have been around for billions of years. They were made in the hearts of exploding stars long before the Earth existed. This means that you are made of recycled materials. When you die, your atoms will disassemble and float away to be part of something else. They might become part of a tree or a rock or a cloud or another person. It is a strange thought, but because atoms last so long and get recycled so often, you almost certainly contain atoms that once belonged to famous people. Mathematical calculations suggest that you probably have about 1 billion atoms in your body that once belonged to William Shakespeare. You also have atoms from Genghis Khan, Beethoven, and Joan of Arc. You also have atoms that were once part of dinosaurs. We are all made of the same stuff, constantly reused. We are just a temporary arrangement of ancient dust. For a long time after Dalton, scientists believed atoms existed, but they couldn't see them. They needed proof. That proof came from a very unlikely place: a botanist looking at pollen. In 1827, a Scottish botanist named Robert Brown was looking through his microscope at some pollen grains floating in water. He noticed something weird. The pollen grains were jittering. They were dancing around, wiggling and shaking, even though the water was perfectly still. Brown was confused. He thought maybe the pollen was alive. But then he tried it with dust and soot and other dead things. They all did the same thing. They danced. This mystery was called Brownian motion. For nearly 80 years, nobody could explain it. Then, in 1905, a young man named Albert Einstein solved the puzzle. Einstein had a very good year in 1905. He solved about 3 massive mysteries of the universe in a few months. Einstein explained that the pollen grains were dancing because they were being hit. The water looked still to the human eye, but down at the microscopic level, the water was made of atoms and molecules that were zooming around like crazy. These invisible water molecules were slamming into the big pollen grains, pushing them left and right. It was the first visible proof that atoms were real and that they were moving. So, by the early 1900s, we knew atoms existed, but we still thought they were solid balls, like Dalton's billiard balls. We didn't know what was inside them. To find out, we needed someone to crack an atom open. That person was Ernest Rutherford. Ernest Rutherford is one of the greatest heroes of science. He was born in New Zealand, far away from the centers of science in Europe. He grew up on a farm, digging potatoes, but he was a genius. He won a scholarship to Cambridge University in England, and later he became a professor at Manchester University, the same city where John Dalton had lived. Rutherford was not a quiet, shy scientist. He was loud. He was big. He had a booming voice that could be heard through the walls of the laboratory. He was full of energy and confidence. He was also terrible at math, which is funny for a physicist. He often needed help with his calculations, but he had an instinct for experiments that was better than anyone else's. He won the Nobel Prize in Chemistry in 1908. This actually annoyed him a little bit. Rutherford was a physicist, and he looked down on chemistry. He once famously said, "All science is either physics or stamp collecting." So, when he won the prize for chemistry, he joked that it was the quickest transformation he had ever seen, from a physicist to a chemist in one day. Rutherford was interested in radioactivity. He wanted to know what happened when radioactive things fell apart. To study this, he designed an experiment that is now famous. It is called the gold foil experiment. The experiment was actually performed by two of his assistants, Hans Geiger, who later invented the Geiger counter, and a young student named Ernest Marston. They set up a machine that shot tiny particles, called alpha particles, like bullets. They aimed these bullets at a sheet of gold foil. The gold foil was incredibly thin, so thin that it was almost transparent. It was only a few atoms thick. The idea was simple. If atoms were soft, solid balls, like the plum pudding model that was popular at the time, the heavy alpha bullets should punch right through the gold foil. It would be like shooting a machine gun at a bowl of pudding. The bullets might slow down a little, but they would go straight through to the other side. So, Geiger and Marston sat in a dark room. They shot the alpha particles at the foil. Behind the foil, they had a special screen that would flash with a tiny spark of light whenever a particle hit it. Their job was to count the sparks. It was boring work. They had to sit in the dark for hours, letting their eyes adjust, waiting for tiny flashes. Most of the particles did exactly what they expected. They went straight through the gold foil and hit the screen behind it. But then, something impossible happened. Every once in a while, maybe 1 in 8,000 times a particle didn't go through. Instead, it bounced back. It hit the gold foil and ricocheted right back toward the shooter. When Geiger told Rutherford this, Rutherford was shocked. He later said it was the most incredible event of his life. He said, "It was as distinct a shock as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. How could a bullet bounce off tissue paper?" Rutherford thought about it for days. Finally, he realized the answer. The atom was not a solid ball of pudding. It was mostly empty space. But right in the center, there was a tiny, incredibly hard knot of matter. He called this hard center the nucleus. Rutherford realized that almost all the mass of the atom was concentrated in this tiny nucleus. The rest of the atom was just a cloud of lightweight electrons floating around it. Because the nucleus is so small, most of the alpha particles missed it. They flew through the empty space of the atom, like a bird flying through an open window. That is why most of them went straight through the foil. But occasionally, just by bad luck, an alpha particle would hit the nucleus head-on. Because the nucleus was so heavy and hard, the particle would bounce off. This gave us the model of the atom we still use in school today, a nucleus in the middle, with electrons orbiting around it, like planets orbiting the sun. But there is a detail about this model that is very hard to comprehend: the scale. The relative size of the nucleus compared to the atom is insane. Imagine a sports stadium, like a giant football stadium. Imagine that the stadium is an atom. If you wanted to find the nucleus, you would have to go to the center of the field and place a small marble on the grass. That marble is the nucleus. The electrons, meanwhile, would be tiny specks of dust buzzing around in the highest seats of the stands. Everything else, the whole field, the rows of seats, the air inside the stadium, is just empty space. This is the most disturbing thing about atoms. They are almost entirely empty. Since everything is made of atoms, and atoms are mostly empty, that means you are mostly empty. If you took all the empty space out of your body, If you squeezed all your nuclei together until they touched, you would shrink down to a size smaller than a grain of salt. You would still weigh the same amount, say 150 pounds, but you would be invisible to the naked eye. This is true for everything. The chair you are sitting on is 99.999999% empty space. The floor is empty space. The planet Earth is mostly empty space. So, why don't you fall through the chair? If you are empty space and the chair is empty space, why don't you just pass through each other like ghosts? The answer is electricity. The electrons whizzing around the outside of the atom create a negative electrical charge. The electrons in your pants are negatively charged. The electrons in the chair are negatively charged. As we know from magnets, like charges repel. So when you sit down, the electrons in your body push against the electrons in the chair. You are not actually touching the chair. You are floating on a tiny cushion of electrical repulsion. You are hovering about 100 millionth of a centimeter above the seat. You have never actually touched anything in your entire life. Rutherford's discovery of the nucleus was brilliant, but it created a new problem. A big one. According to the laws of physics at the time, this new atom shouldn't work. If the electrons are negative and the nucleus is positive, they should attract each other. The electrons should spiral inward and crash into the nucleus. The whole atom should collapse in a tiny fraction of a second. This meant that according to the best science of 1910, the universe shouldn't exist. All matter should instantly self-destruct. Obviously, the universe does exist. So, the physicists knew they were missing something. They needed a new set of rules to explain how the tiny world of the atom worked. This led to the strangest, most confusing, and most magical branch of science ever invented: quantum mechanics. And the story of quantum mechanics begins with a polite, quiet Danish man named Niels Bohr. Bohr was a genius, but he was very different from Rutherford. Rutherford was loud and boisterous. Bohr was soft-spoken and mumbled. He was famous for taking a long time to finish a sentence, but when he finally finished the sentence, it was usually profound. Bohr looked at Rutherford's model and said, "We have to stop thinking about atoms like they are tiny solar systems. They don't follow the rules of normal objects. They follow their own weird rules." Bohr proposed a daring idea called the quantum leap. He said that electrons do not fly through space like airplanes. Instead, they exist in specific layers or shells around the nucleus. Think of the atom like a staircase. An electron can stand on the first step, or it can stand on the second step. But it cannot stand in the empty air between the steps. It is physically impossible for the electron to be in the spaces between the layers. The weird part is how the electron moves from one step to another. When an electron jumps from the first shell to the second shell, it does not travel through the space in between. It simply ceases to exist on the first shell and simultaneously appears on the second shell. It teleports. It disappears from here and reappears there without ever passing through the middle. This is the famous quantum leap. In everyday language, we use this phrase to mean a big, important change. But in physics, it means something that happens instantly, and without any visible path. This idea solved the problem of the collapsing atom. The electron cannot spiral into the nucleus because there is no step for it to stand on down there. The bottom shell is the lowest ground it can occupy. It is safe. However, this solution opened the door to a world of confusion. If matter can teleport, and if things can be in two places at once, then the universe is not the solid, reliable place we thought it was. Another scientist, a German named Werner Heisenberg, made it even more complicated. He realized that we can never really know exactly where an electron is. He came up with the uncertainty principle. Heisenberg said that an electron is not really a particle, like a marble. It is more like a cloud. It is a smear of probability. It isn't in one specific spot. It is kind of everywhere, in its shell at the same time. It only decides to be in one specific spot when we look at it. This drove older scientists crazy. Einstein hated it. He famously said, "God does not play dice with the universe." He wanted the world to be predictable. He wanted an electron to be a thing with a specific address. But the new quantum mechanics said, no, the world is just a game of chance. The electron might be here, or it might be there, and you cannot know for sure until you check. Despite how crazy it sounds, this theory is the basis of our modern world. It explains how lasers work, how computer chips work, and how the sun burns. If atoms didn't act this way, we wouldn't be here. By the 1930s, physicists had a pretty good picture of the atom. They knew about the electron on the outside. They knew about the proton in the nucleus, but there was still one piece of the puzzle missing. The math didn't add up. Hydrogen is the simplest atom. It has one proton in the middle and one electron on the outside. Helium is the next simplest. It has two protons and two electrons. So, logic suggests that a helium atom should weigh exactly twice as much as a hydrogen atom. 2 is double 1. But when they weighed the atoms, helium was actually 4 times heavier than hydrogen. Where was the extra weight coming from? There was some mysterious stuff hidden in the nucleus that added weight but didn't have any electrical charge. Since it had no charge, it was invisible to their electrical experiments. It took until 1932 for a man named James Chadwick to find it. He discovered the neutron. The neutron is a particle that sits in the nucleus right next to the protons. It is about the same size and weight as a proton, but it is neutral. It doesn't push or pull electrically. It just acts as a kind of heavy glue. The discovery of the neutron completed the family. Now we knew all the players. Protons. Heavy, positive charge, live in the middle. Neutrons. Heavy, no charge, live in the middle. Neutrons. Heavy, no charge. Electrons, tiny negative charge, fly around the outside. This simple list explains almost everything in the universe. The number of protons decides what an element is. If an atom has 1 proton, it is hydrogen. If it has 6, it is carbon. If it has 79, it is gold. You can turn lead into gold just by taking away 3 protons. Of course, doing that is incredibly difficult and expensive. but it is physically possible. The number of neutrons decides the isotope. An isotope is just a heavy or light version of the same element. For example, most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. But some carbon atoms have 6 protons and 8 neutrons. We call this carbon-14. It is still carbon. It still looks and acts like carbon, but it is a little bit heavier. This knowledge about isotopes and neutrons became very important for answering one of the biggest questions humans have ever asked. How old is the Earth? For most of history, nobody knew. People just guessed. In 1650, an Irish archbishop named James Ussher decided to figure it out by reading the Bible. He looked at the family trees in the Old Testament, who begat whom, and added up the ages. He made a very precise calculation. He announced that the Earth was created at midday on October 23rd, 4004 BC. For a long time, people accepted this. It meant the Earth was only about 6,000 years old. It was a comfortable, human-sized number. But when scientists started looking at rocks and mountains, they realized 6,000 years wasn't enough time. You can't build a mountain range or carve the Grand Canyon in 6,000 years. The Earth looked ancient. In the 1800s, a very famous scientist named Lord Kelvin tried to use physics to find the answer. Kelvin was a brilliant man. The temperature scale, Kelvin, is named after him. He assumed that the Earth started as a ball of hot, molten rock and had been cooling down ever since. He calculated how long it would take for a rock that size to cool down to the temperature it is today. He did the math and announced that the Earth was somewhere between 20 million and 400 million years old. Later, he refined it to about 24 million years. Kelvin was very confident, but he was wrong. He was wrong because he didn't know about the new discovery we just talked about, the atom. Specifically, he didn't know about radioactivity. Inside the Earth, there are radioactive elements like uranium and thorium. As these heavy atoms fall apart, they release heat. They are like tiny little furnaces burning inside the rocks. This means the Earth isn't just a cooling potato. It has its own internal heater. This kept the Earth hot for billions of years, longer than Kelvin thought possible. But radioactivity didn't just explain the heat. It also gave scientists a clock. Here is how the clock works. Radioactive atoms are unstable. They want to turn into something else. Over time, a uranium atom will shoot off particles and eventually turn into a lead atom. We don't know when a specific atom will decay. It's random, but we do know exactly how long it takes for a group of atoms to decay. We call this the half-life. For example, let's say you have a lump of uranium. The half-life is the time it takes for half of that uranium to turn into lead. It is a constant, steady process. It ticks along perfectly, regardless of heat, cold, or pressure. So, if you find a rock, you can measure how much uranium is inside it and how much lead is inside it. If there is a lot of uranium and no lead, the rock is new. If there is a mix of both, the rock is old. By comparing the ratio, you can calculate exactly when the rock was formed. This sounds perfect, but in practice, it was incredibly difficult to do. The man who finally solved it was a young geochemist named Claire Patterson. In the late 1940s, Patterson was a student at the University of Chicago. His professor gave him an assignment: measure the age of the Earth using lead isotopes. It sounded like a straightforward school project. The professor thought it might take a year or two. It took Patterson 7 years of torture. The problem wasn't the math. The problem was the environment. Patterson was trying to measure tiny amounts of lead in rock samples, but he kept getting weird results. One day the sample would show a certain amount of lead, and the next day it would show a huge amount. The numbers were jumping all over the place. He realized that his samples were being contaminated. There was lead everywhere. There was lead in the dust floating in the air. There was lead in the paint on the walls. There was lead in the water pipes. Even the makeup on people's faces contained trace amounts of lead. Every time he tried to test a rock, invisible specks of lead from the room would fall into his sample and ruin the experiment. It was like trying to count the number of grains of sugar in a bowl while someone is pouring a bag of sugar over your head. Patterson became obsessed with cleanliness. He realized he needed a super clean laboratory. He moved to Caltech in California and built the world's first clean room. He covered everything in plastic. He washed the floors with acid. He made sure the air was filtered. He would strip naked and put on a special Tyvek suit before entering the room. He scrubbed the walls every day. Finally, in this ultra-pure environment, he was able to measure the lead without any contamination. He used a meteorite to do the measurement. Meteorites are leftover building blocks from when the solar system was formed. They are the same age as the Earth, but they have been floating in space, so they haven't been melted and recycled like the rocks on Earth. He took his meteorite sample into his clean room, dissolved it in acid, and ran it through his machine. In 1953, he got the number. He was so excited that he drove straight to his parents' house in Iowa. He told his mother that he was the first person in the history of the world to know exactly how old the world was. The number was 4.55 billion years. That number still stands today. The Earth is 4.55 billion years old. But Patterson's story didn't end there. In fact, his struggle with lead in the lab made him curious about lead in the real world. He started to wonder, if there is so much lead in my lab that it ruins my experiments, where is it all coming from? He started testing things outside the lab. He tested seawater. He tested ice from Greenland. He tested the blood of people. What he found was terrifying. He discovered that the atmosphere of the Earth was being poisoned. The natural level of lead in the air should be almost zero, but Patterson found that the levels were hundreds of times higher than natural. He traced the source to one specific invention: leaded gasoline. In the 1920s, car companies, led by General Motors, had started adding a chemical called tetraethyl lead to gasoline. It made engines run smoother. It stopped the knocking sound in car engines. The inventor, Thomas Midgley, a man who had a disastrous effect on the atmosphere. He also invented CFCs, which destroy the ozone layer. Knew lead was poisonous, but it was profitable. For 40 years, every car in the world had been spewing toxic lead dust out of its tailpipe. Patterson realized that this wasn't just a science problem. It was a public health crisis. Lead is a neurotoxin. It damages the brain. It makes people crazy. It lowers the IQ of children. And thanks to leaded gas, we were spraying it into the face of every child in America. Patterson decided to fight. He wrote papers saying that leaded gas should be banned. This made him very unpopular. The oil companies were powerful. They tried to buy him off. They offered him money to shut up. When he refused, they tried to get him fired. They pressured the university. They got his research funding cut off. But Patterson was stubborn. He was the man who had spent 7 years scrubbing floors to measure a rock. He didn't give up easily. He spent the next 20 years fighting the oil industry. He collected data from the bottom of the ocean and the top of the ice caps to prove that lead pollution was recent and man-made. Finally, he won. In the 1970s and 80s, the United States began to phase out leaded gasoline. Other countries followed. Because of Claire Patterson, the levels of lead in the blood of Americans have dropped by 80%. He didn't just tell us how old the Earth is, he made it a safer place to live. So, now we know the age of our planet, 4.5 billion years. But this brings up the next question. If the Earth is a floating rock in space, what is beneath our feet? What is inside the Earth? We know more about the surface of Mars than we know about the inside of our own planet. The deepest hole humans have ever dug is called the Kola Super Deep Borehole in Russia. They spent years drilling. They wanted to go all the way through the crust. But they only made it about 7.5 miles down. That sounds deep, but the Earth is nearly 4,000 miles to the center. If the Earth were an apple, the Kola hole didn't even break through the skin. So, how do we know what is down there? We know what is inside the Earth not by looking, but by listening. When an earthquake happens, it does not just shake the ground where the buildings fall down. It sends powerful waves of energy traveling through the entire planet. These waves ring the Earth like a bell. By listening to the tone of that ring, scientists can figure out what the bell is made of. The people who study these waves are called seismologists. In the early 1900s, they realized that earthquake waves behave in very specific ways. There are two main types of waves. The first type is called a P wave, primary wave. P waves work like a concertina or a slinky. They push and pull. They compress the rock and then expand it. These waves are fast, and they can travel through anything solid rock, liquid water, or gas. The second type is called an S wave, secondary wave. These are slower. They move side to side, like a snake wiggling on the ground. But S waves have a weakness. They cannot travel through liquid. If they hit a pool of liquid, they simply stop. This difference is the key to seeing inside the Earth. In 1906, a British geologist named Richard Dixon Oldham was studying the records of earthquakes from around the world. He noticed something strange. When a big earthquake happened on one side of the world, the P waves would travel through the center of the Earth and arrive on the other side. But the S waves, the wiggling ones, never showed up on the other side. They just disappeared. Oldham realized that there was a shadow zone where the S waves were blocked. This meant there had to be something liquid deep inside the Earth that was stopping them. He had discovered the Earth's core. We now know that the Earth is built in layers, like a giant onion. On the outside where we live is the crust. The crust is incredibly thin. If the Earth were the size of a basketball, the crust would be thinner than a sheet of paper. Under the oceans, it is only about 5 miles thick. Under the continents, it is a bit thicker, maybe 25 miles, but compared to the size of the planet, it is nothing. It is just a fragile skin of dried rock. Below the crust is the mantle. This is a thick layer of heavy rock that goes down for about 1,800 miles. The mantle is solid, but it is hot and under so much pressure that it can move slowly, like very thick, majestic putty. Below the mantle is the outer core. This is the layer Oldham found. It is a sea of liquid iron and nickel. It is incredibly hot, and it spins. This spinning liquid metal acts like a giant electrical generator. It creates the magnetic field that surrounds the Earth and protects us from the sun's radiation. Without this liquid layer, Earth would be a dead rock like Mars. Finally, right in the center, is the inner core. This was discovered later by a brilliant Danish seismologist named Inga Lehmann. She realized that while the outer core is liquid, the very center is crushed so hard by the weight of the world that it is solid. It is a ball of solid iron, about the size of the moon, spinning in the center of the planet. It is as hot as the surface of the sun. So, we are living on a thin crust, floating on top of a hot, churning soup of rock and metal. And because the stuff underneath is moving, the ground beneath our feet is moving too. This brings us to one of the most surprising facts in science. The ground is not stable. The continents, Africa, America, Europe, are moving. They are wandering across the face of the Earth like rafts on a pond. Today, every school child learns about plate tectonics. We look at a map of the world and we can see it immediately. If you look at the east coast of South America and the west coast of Africa, they look like puzzle pieces. The bulge of Brazil fits perfectly into the dent of Africa. It seems obvious that they were once attached and have drifted apart. But for a very long time, scientists refused to believe this. They thought it was just a coincidence. They believed the Earth was solid and immovable. The man who changed this was a German meteorologist named Alfred Wegener. Wegener was not a geologist. He studied weather. But he was a man who loved adventures and noticed details. In the early 1900s, he looked at the maps and saw the puzzle pieces. He thought, this cannot be an accident. He started looking for evidence. He found that there were fossils of the same ancient animals in Brazil and in Africa. These were small land animals that could not swim across an ocean. How did they get to both places? The only answer was that the places used to be connected. He also looked at mountains. He found that the rock formations in Scotland matched the rock formations in the Appalachian Mountains in America. If you pushed North America and Europe back together, the mountains formed a single, continuous line. He found evidence of ancient glaciers in places that are now hot deserts, and he found coal, which is made from tropical jungle plants, in Antarctica. In 1912, Wegener proposed his theory. He called it continental drift. He said that long ago, all the continents were bunched together in one giant supercontinent, which he called Pangaea, meaning all Earth. Then they broke apart and drifted to where they are now. It was a brilliant idea. It explained everything. It explained the fossils, the mountains, and the shapes of the coastlines. but the scientific community hated it. They didn't just disagree with him, they ridiculed him. They called his idea delirious ravings. One famous geologist said that anyone who believed in floating continents should be put in an asylum. The problem was that Wegener couldn't explain how the continents moved. He was a weatherman, not a physicist. He knew they moved, but he didn't know the mechanism. He suggested maybe the rotation of the Earth pushed them, or the tides. The geologists calculated the forces and said, "No, that's impossible. The continents are made of solid granite. The ocean floor is made of dense basalt. You can't just push a continent through the ocean floor. It would be like trying to push a stick of butter through a brick wall. The butter would break." Goodness. Because he couldn't explain the mechanics, they threw out his whole theory. Wegener spent the rest of his life trying to find proof. He was a brave man. He led expeditions to Greenland to study the ice and the weather. On his fourth trip to Greenland in 1930, he went out onto the ice sheet to deliver supplies to his colleagues. It was a brutal trip. Temperatures dropped to -60 degrees. On his way back from the camp, Alfred Wegener died on the ice. He was 50 years old. He was buried in the snow by his companion, who then disappeared and was never seen again. Wegener died thinking he was a failure. He never knew that he was right. It took another 30 years for the world to catch up to him. During World War II, the military needed to understand the ocean floor to hide their submarines. They developed new technologies like sonar to map the bottom of the sea. Before this, people thought the ocean floor was just a flat, muddy plain. When they turned on the sonar, they were shocked. The ocean floor was not flat. It was rugged. It was full of canyons and volcanoes. Most importantly, they found a giant mountain range running down the middle of the Atlantic Ocean. It is called the Mid-Atlantic Ridge. It winds its way round the globe like the seam on a baseball. In the 1960s, scientists studied this ridge. They found that it was actually a crack in the Earth. Hot magma from deep inside the mantle was pushing up through the crack. It would cool and harden to form new rock. This was the engine that Wegener had missed. The continents don't plow through the ocean floor like a ship pushing through ice. The ocean floor itself is moving. The Earth creates new crust at the ridges, and this new crust pushes the old crust aside. It acts like a giant conveyor belt. As the Atlantic Ocean gets wider, because of the new rock appearing in the middle, it pushes America and Europe further apart. Suddenly, everything made sense. The Earth's surface is broken into about a dozen giant plates. Some carry oceans, some carry continents. They float on the hot, moving mantle below. Where they crash into each other, they push up mountains like the Himalayas. Where they pull apart, they create oceans. Where they slide past each other, they cause earthquakes, like in California. Alfred Wegener was vindicated. He is now considered one of the fathers of modern geology. So, we have a planet that is hot inside, moving on the outside, and covered in life. But life itself is a very strange thing. For a long time, we didn't know how life began or how it worked. We knew that living things were different from rocks, but we didn't know why. We needed to understand the machinery of life. We needed to find the molecule that holds the instructions for building a human being. We needed to find DNA. The story of DNA is usually told as the triumph of two men, James Watson and Francis Crick, and they were certainly brilliant. But their discovery was built on the work of many others, including a quiet woman who was ignored for decades. DNA stands for deoxyribonucleic acid. It had actually been discovered way back in 1869 by a Swiss doctor who found it in the pus on discarded surgical bandages, which is gross, but science is often gross. But for a long time, nobody thought it was important. It just seemed like a boring white powder. Most scientists thought the secret of life must be proteins. Proteins are complex and varied. DNA seemed too simple. It only has 4 parts, 4 little chemical bases which we call A, T, C, and G. It seemed impossible that you could write the recipe for a human brain or a peacock's tail using an alphabet of only 4 letters. But in the 1950s, the race was on to figure out the structure of this molecule. In Cambridge, England, there were 2 unlikely partners. James Watson was a young, brash American. He was only 23 years old. He was arrogant, messy, and didn't really like to do hard work. He had gone to Europe partly because he wanted to meet girls. Francis Crick was older, 35. He was British, talkative, and brilliant, but he hadn't actually finished his PhD yet. He talked so much that his bosses at the university sometimes put him in a separate room so he wouldn't disturb the other scientists. They didn't do experiments. They didn't mix chemicals or look through microscopes. Instead, they built models. They used metal rods and cardboard cutouts to try to guess the shape of the molecule. They treated it like a jigsaw puzzle. But to solve the puzzle, they needed a clue. They needed to see what the molecule looked like. That clue came from London, from a laboratory at King's College. There, a woman named Rosalind Franklin was working. Rosalind Franklin was a serious, precise scientist. She was an expert in a technique called X-ray crystallography. This involves shooting X-rays at a crystal and capturing the shadow it casts on film. It is incredibly difficult work. Franklin took the best picture of DNA ever seen. It is known as photograph 51. The picture showed a blurry X shape. To the untrained eye, it looks like nothing. But to an expert, that X meant one thing: a helix, a spiral. Franklin was cautious. She wanted to check her math before she announced the answer. She put the photograph in her drawer. But her colleague, Maurice Wilkins, who she did not get along with, took the photograph without her permission and showed it to Watson. When Watson saw the picture, his jaw dropped. He knew immediately what it meant. He rushed back to Cambridge and told Crick. They started building a new model. They realized that DNA wasn't just a single spiral. It was a double helix. It looked like a twisted ladder. The sides of the ladder were the backbone of the molecule. The rungs of the ladder were the 4 chemical bases pairing up, and always paired with T. C, always paired with G. This was the secret mechanism. Because the pairs were always the same, the molecule could copy itself. If you unzip the ladder down the middle, you would have 2 half ladders. Each half could grab new chemicals floating nearby to rebuild the missing side. 1 DNA molecule became 2. This is how life reproduces. This is how a single cell becomes a baby. Watson and Crick published their discovery in 1953. They famously walked into a pub in Cambridge called the Eagle and announced to the drinkers that they had found the secret of life. They won the Nobel Prize in 1962. Maurice Wilkins shared it with them. Rosalind Franklin did not. She had died of ovarian cancer 4 years earlier, at the age of 37. The Nobel rules say the prize cannot be given to someone who has died. So she was left out of history for a long time. Watson even wrote a book later where he made fun of her, calling her Rosie and criticizing her hair and her clothes. It was only years later that people realized she had provided the key piece of evidence. So now we have the Earth, the atoms, and the code of life. But how did life actually begin? It turns out that life is incredibly tough. It can survive almost anything. But it is also incredibly fussy about where it starts. To understand how life began, we have to look at what the Earth was like in the beginning. It was not a nice place. If you stepped out of a time machine onto the early Earth about 4 billion years ago, you would die instantly. There was no oxygen to breathe. The air was filled with poisonous gases like methane, ammonia, and sulfur. The surface was blasted by volcanoes and bombarded by meteorites. It was a hot, toxic, violent world. Yet somehow, in the middle of this nightmare, chemistry turned into biology. Dead atoms decided to become alive. We still don't know exactly how this happened. It is the biggest mystery in science, but we have some clues. In 1953, the same year, Watson and Crick found DNA. A young graduate student named Stanley Miller performed a famous experiment at the University of Chicago. He wanted to see if he could recreate the primordial soup of the early Earth. Miller took 2 glass flasks and connected them with glass tubes. In the lower flask, he put water to represent the ancient ocean. In the upper flask, he put a mixture of gases, methane, ammonia, and hydrogen, to represent the ancient atmosphere. Then he added sparks of electricity to simulate lightning. He let the machine run for a week. The water turned yellow, then pink, and finally a deep, muddy red. When Miller analyzed the muddy water, he found something amazing. The flask was full of amino acids. Amino acids are the building blocks of life. They are the Lego bricks that make up proteins. Miller proved that you don't need a miracle to make the basic ingredients of life. You just need some gas, some water, and a little bit of lightning. It happens naturally. This made everyone very excited. They thought, if making the bricks is this easy, maybe making the house is easy too. But they were wrong. Making amino acids is easy. Making a living protein is incredibly hard. A protein is a long chain of amino acids strung together in a very specific order. It is like a sentence. If you scramble the letters of a sentence, it becomes nonsense. It is the same with proteins. To make a working protein like collagen, which holds your skin together, or hemoglobin, which carries oxygen in your blood, you have to arrange hundreds of amino acids in the exact right sequence. The odds of this happening by accident are almost zero. Imagine you have a giant slot machine with 20 wheels, because there are 20 types of amino acids. To get a protein, you have to spin the wheels and get the winning combination. But you don't just have to win once, You have to win hundreds of times in a row, without a single mistake. Mathematicians have calculated the odds. The chance of a typical protein assembling itself by random chance is roughly 1 in 10 to the power 260. That is a 1 followed by 260 zeros. To put that in perspective, there are only 10 to the power of 80 atoms in the entire universe. So, statistically, life should not exist. It is a mathematical impossibility. A famous astronomer named Fred Hoyle once said that the accidental formation of life is about as likely as a tornado sweeping through a junkyard and accidentally assembling a fully functioning Boeing 747 jumbo jet. And yet, here we are. This suggests one of two things. Either we are incredibly lucky, the winners of the biggest lottery in the universe, or there is some chemical law we don't understand yet that pushes matter toward life. Maybe the universe wants to be alive. Whatever the reason, life did start. And it started very quickly. We have found rocks in Greenland that are 3.85 billion years old. We have now been still several years old. These rocks contain traces of carbon that look like they were processed by living things. This means that almost as soon as the Earth cooled down enough to have solid ground, life appeared. But for a very long time, life didn't do much. For the first few billion years, the Earth was ruled by bacteria. They were the only things here. They lived in the water, eating chemicals and sunlight. These ancient bacteria were tough. They formed sticky mats called stromatolites. You can still see living stromatolites today in a few places, like Shark Bay in Australia. They look like big, slimy rocks sitting in the shallow water. But if you look closely, they are cities built by billions of microscopic creatures. For 2 billion years, these bacteria were the kings of the world, but they were simple. They were single cells. They didn't have a nucleus. They just floated and divided, floated and divided. Then, about 3.5 billion years ago, a specific type of bacteria called cyanobacteria invented something new. They invented photosynthesis. They figured out how to use sunlight to break apart water molecules. They kept the hydrogen for food and spit out the oxygen as waste. This was the most important pollution event in history. Before this, there was no oxygen in the air. Oxygen is actually a very aggressive gas. It makes iron rust and wood burn. To the ancient bacteria used to living in a sulfur world, oxygen was a deadly poison. As the cyanobacteria pumped more and more oxygen into the atmosphere, they started a mass extinction. The old world died. The anaerobic, no-oxygen bacteria were forced to hide in the deep mud, where they still live today. But for the new life, oxygen was a gift. It was a high-energy fuel. With oxygen, cells could burn food more efficiently and grow bigger, but they couldn't get too big. Life was still stuck at the single-cell stage. To take the next step, something drastic had to happen. This is the story of the Great Team-Up. About 1.5 billion years ago, a big predatory bacterium was swimming around, looking for a snack. It found a smaller bacterium and swallowed it whole. Usually the big bacterium would digest the small one, but this time something different happened. The little bacterium didn't die. It stayed alive inside the big one. and it made a deal. The little bacterium said in chemical language, "If you don't eat me, I will generate energy for you. I will be your power plant." The big bacterium agreed. It provided protection and food, and the little bacterium provided supercharged energy. This partnership was so successful that it changed the world. The little bacterium eventually became what we call a mitochondrion. You have them in your body right now. Every cell in your body contains tiny, bean-shaped structures that generate your energy. They have their own separate DNA, different from yours. They are the descendants of that ancient bacteria that got swallowed billions of years ago. You are basically a colony of ancient bugs working together. This new, complex type of cell is called a eukaryote. Once the eukaryotic cell was invented, life could get complicated. Cells could start sticking together. They could specialize. One cell could say, "I'll be skin," and another could say, "I'll be a nerve." But even then, life took its time. For another billion years, often called the boring billion, nothing much happened. It was just slime and algae. Then, quite suddenly, about 540 million years ago, biology went crazy. This event is called the Cambrian explosion. In a very short amount of time, geologically speaking, the Earth went from being a world of simple blobs to a world of complex animals. Creatures developed legs, eyes, mouths, shells, and teeth. We know this because of a famous fossil site in Canada called the Burgess Shale. In 1909, a paleontologist named Charles Doolittle Walcott was walking in the Canadian Rockies. He stumbled upon a piece of shale rock full of weird fossils. He dug up thousands of them. The animals in the Burgess Shale are like nothing alive today. There was a creature called Opabinia that had 5 eyes and a nozzle like a vacuum cleaner. There was a giant predator called Anomalocaris that looked like a shrimp crossed with a nightmare. There was a spiky worm called Hallucigenia that was so weird scientists originally reconstructed it upside down, thinking its spines were its legs. It was a time of experimentation. Nature was trying out every possible body shape to see what worked. Many of these designs failed and went extinct, but some survived. One of the creatures in the Burgess Shale was a tiny worm-like thing called Picaia. It wasn't very impressive, but it had a stiff rod running down its back. It was the first creature with a backbone. That tiny worm is your great-great-great-grandmother. It is the ancestor of all fish, lizards, dinosaurs, and humans. If Picaia had been eaten by an Anomalocaris, you wouldn't be reading this right now. So, the oceans were full of life, but the land was still empty. It was just bare rock and sand. Moving to land was a huge challenge for life. In the ocean, you don't need strong bones because the water supports your weight. You don't need to worry about drying out. On land, gravity crushes you, and the sun burns you. The first pioneers were plants. Mosses and lichens crept out of the water and started turning the rock into soil. Then came the bug scorpions and millipedes. Then, about 375 million years ago, a fish decided to take a walk. This fish is known as Tiktaalik. It was a strange creature. It had scales and gills like a fish, but it also had a neck and strong fins that worked like legs. It lived in shallow swamps. We think Tiktaalik started pulling itself out of the water to escape predators or to find food. It could do push-ups to lift its head above the water. Slowly, over millions of years, those fins turned into legs. The swim bladder turned into lungs. The descendants of Tiktaalik became the amphibians, frogs, and salamanders. They could walk on land, but they had to go back to the water to lay their eggs. Their eggs were soft and jelly-like. If they laid them on dry land, they would dry up and die. To really conquer the land, animals needed a new invention, the waterproof egg. This was the amniotic egg. It had a hard shell that kept the water inside. It was like a private little ocean for the baby to grow in. With this invention, reptiles could leave the water behind completely. They could walk into the desert. They could climb mountains. And so, the age of the reptiles began. This led, eventually, to the most famous animals of all, the dinosaurs. But before we talk about dinosaurs, we have to talk about how fragile life is. We think of the history of life as a straight line of progress, from bacteria to worms to fish to lizards to us. But it wasn't a straight line. It was a terrifying obstacle course. The Earth has tried to kill life many, many times. There have been 5 great mass extinctions in history. These are times when the world went wrong and most species on Earth died. The worst one happened 250 million years ago, just before the dinosaurs appeared. It is called the Permian extinction, or the Great Dying. We still aren't 100% sure what caused it. It was probably massive volcanic eruptions in Siberia that lasted for thousands of years. The volcanoes pumped so much carbon dioxide and toxic gas into the air that the planet cooked. The oceans became acidic. It was an apocalypse. 95% of all marine species died. 70% of land species died. The Earth was almost wiped clean. It took millions of years for life to recover. But in a grim way, mass extinctions are necessary for progress. They clear the board. They kill off the old, successful animals and make room for new, scrappy underdogs to take over. The Great Dying cleared the way for the dinosaurs. And the dinosaurs ruled for an incredibly long time, about 165 million years. We often think of dinosaurs as failures because they went extinct. But that is unfair. They were incredibly successful. Humans have only been around for about 200,000 years. The dinosaurs lasted almost 1,000 times longer than we have. They dominated every continent, but then their luck ran out. 66 million years ago, a rock the size of a mountain was floating through space. It was an asteroid, about 6 miles wide. It was traveling at 40,000 miles per hour. It was headed for a place we now call Mexico. If the asteroid had arrived 20 minutes later, the Earth would have rotated slightly. The rock would have hit the deep ocean, the Pacific or Atlantic. The water would have absorbed much of the impact. There would have been huge tsunamis that the dinosaurs might have survived, but it didn't hit the deep ocean. It hit the shallow water of the Yucatan Peninsula. The impact was unimaginable. It released the energy of 1 billion nuclear bombs. It blasted a hole in the Earth 20 miles deep. It turned the bedrock into liquid. Debris was thrown halfway to the moon. As the rocks fell back down to Earth, they heated up the atmosphere. The air became as hot as an oven. Forests across the world spontaneously burst into flames. Then came the darkness. The dust and smoke blocked out the sun for months, maybe years. The plants died. The plant eaters died. The meat eaters died. The dinosaurs were gone. Except for the birds, which are their direct descendants. But in the ashes of that burning world, something survived. Small, furry, frightened little creatures were hiding in burrows underground. They ate insects and roots. They were the mammals. While the dinosaurs were in charge, mammals had to stay small and hide. We were the underdogs. But when the asteroid hit, being small was an advantage. The big dinosaurs couldn't find enough food, but the little mammals could survive on scraps. With the monsters gone, the mammals came out of their holes. They grew bigger. They took over the world. They put in the world of oceans. And eventually, one group of these mammals decided to live in the trees. They developed grasping hands and forward-facing eyes. They were the primates. This brings us to the final chapter of our biological history, the rise of us. But humans are a very recent addition to the story. If you imagine the 4.5 billion years of Earth's history as a single 24-hour day, humans appear only in the last seconds before midnight. For almost the entire day, we weren't here. To understand how we got here, we have to look at the Ice Ages. For most of the dinosaur era, the Earth was hot. There was no ice at the poles. Palm trees grew in Alaska. But in the last few million years, the Earth has cooled down. We are currently living in an ice age. That sounds wrong because it feels warm outside, but scientifically, an ice age is any time when there is permanent ice at the poles. For the last 2.5 million years, the ice has been moving back and forth. Sometimes it grows and covers North America and Europe, glacials. Sometimes it melts back, interglacials. We are currently in a melt-back period. These changing climates forced our ancestors to be smart. When the forests dried up and turned into grasslands in Africa, our ape-like ancestors had to come down from the trees. They had to stand on two legs to see over the tall grass. Walking on two legs is efficient, but it causes problems. It gave us bad backs and knee pain, but it freed up our hands. We could carry things. We could use tools. And most importantly, our brains started to grow. A big brain is a very expensive luxury. In the animal kingdom, brains are rare because they cost so much to run. Your brain is only about 2% of your body weight, but it uses 20% of your energy. It is a greedy organ. It demands constant food. To support a brain this size, our ancestors had to change their diet. They had to switch from eating low-energy grass and leaves to eating high-energy meat. We had to become hunters and scavengers. There was another huge price to pay for being smart: childbirth. As we stood up and learned to walk on two legs, our hips had to change shape. The pelvis became narrower to support our weight efficiently. But at the same time, our heads were getting bigger. This created a terrible engineering conflict. We needed narrow hips to walk, but wide hips to pass a big-headed baby. Nature's solution was to force human babies to be born prematurely. If a human baby stayed in the womb as long as a foal or a calf, its head would be too big to get out. It would kill the mother. So, human babies are born while their brains are still small and soft. This means human infants are completely helpless. A baby zebra can run away from a lion an hour after it is born. A human baby cannot even hold up its own head. This helplessness changed everything. Because babies needed care for years, parents had to stay together. It forced us to become social. It created the family unit. It made us talk to each other. For a long time, there were many different kinds of humans running around. We often see the famous picture of evolution as a single line, a monkey turning into a slouching ape, then a slightly taller ape, and finally a man in a suit. This is known as the march of progress, but it is wrong. Human evolution wasn't a line, it was a bush. There were many branches. At one point, not so long ago, there were at least 4 or 5 different species of humans living on Earth at the same time. There were the Neanderthals in Europe. They were shorter than us, but much stronger. They were incredibly tough. They lived through the deepest freezes of the Ice Age. They hunted woolly mammoths with spears. And surprisingly, their brains were actually bigger than ours. In Asia, there were the Denisovans. We don't know much about them, but we have found their DNA in a cave in Siberia. On a tiny island in Indonesia called Flores, there was a species of tiny humans. They were only 3 feet tall. Scientists nicknamed them hobbits. They lived there until very recently, perhaps as recently as 12,000 years ago. They were hunting tiny elephants and fighting Komodo dragons while our own ancestors were building the first villages. But today, all those other branches are gone. We, Homo sapiens, are the only ones left. Why did we survive while the stronger Neanderthals died? Some people think we killed them. We have a history of being violent, after all. But it is more likely that we just outcompeted them. We were better at communicating. We had better tools. We traded with each other. When times got hard, we could rely on neighbors. The Neanderthals lived in small, isolated groups. We also bred with them. Most people of non-African descent today have about 2% Neanderthal DNA in their blood. So, in a way, they didn't completely disappear. A little bit of them is still walking around inside us. About 100,000 years ago, our specific species moved out of Africa and spread across the globe. We were unstoppable. We learned to make boats and reached Australia 50,000 years ago. We crossed the land bridge from Russia to Alaska and populated the Americas. Wherever we went, the big animals disappeared. In Australia, there used to be wombats the size of rhinoceroses and lizards 20 feet long. Within a few thousand years of humans arriving, they were all gone. In America, there were mastodons, giant sloths, and saber-toothed cats. They vanished too. We are very efficient predators. But for all our hunting and traveling, we were still at the mercy of the weather. 10,000 years ago, the ice drew back. The climate stabilized. This period is called the Holocene. It is the long, warm summer that has allowed civilization to exist. With the ice gone, we did something new. Instead of chasing food, we decided to make the food come to us. We invented agriculture. We took wild grasses like wheat and rice and bred them to have bigger seeds. We took wild wolves and turned them into dogs. We took wild boars and turned them into pigs. Farming allowed us to stay in one place. We built towns. We built walls. We invented writing to keep track of our grain. We invented money. We invented armies. We are. In the blink of an eye, we went from caves to cathedrals. It is a very impressive story. We feel like the masters of the earth. We have paved the planet, dammed the rivers, and lit up the night side of the world with electricity. But we should not get too arrogant. We might think we run the place, but we are really just guests. The true owners of the earth are the things we cannot even see. We live in a world of microbes. Bacteria, viruses, and fungi were here billions of years before us, and they will be here billions of years after we are gone. They are the most abundant life forms on the planet. If you weighed all the ants, cows, humans, and elephants on Earth, the bacteria would still weigh more than all of us combined. They are everywhere. They are in the soil, in the air, in the deepest ocean trenches, and inside rocks miles underground. They are also inside you. You are a walking colony. There are about 30 trillion human cells in your body, but there are about 39 trillion bacterial cells living in and on you. By the numbers, you are more bacteria than human. They are on your skin, in your eyelashes, and mostly in your gut. We tend to think of bacteria as germs, bad things that make us sick. But most of them are neutral, and many are essential. We couldn't survive without them. The bacteria in your stomach digest your food. They make vitamins that you can't make yourself. They train your immune system. They protect you from other bad bacteria. However, the relationship is tricky. Because we live in such a crowded world, we are constantly under attack. Throughout history, the biggest killer of human beings hasn't been lions or wars or starvation. It has been disease. Smallpox, for example, was a horror. It killed roughly 300 million people in the 20th century alone. That is more than all the wars in history combined. When Europeans arrived in the Americas, they brought smallpox with them. The native people had no immunity. It swept across the continents like a forest fire. It is estimated that 90% of the population of the Americas died from disease before they even saw a white man. Civilizations collapsed simply because everyone died of the flu. We have only recently started to win this war. In 1928, a Scottish scientist named Alexander Fleming was a bit messy. He went on vacation and left a petri dish of bacteria sitting out on his bench. When he came back, he saw that some mold had grown on the dish. He was about to throw it away, but he noticed something interesting. Around the mold, the bacteria were dead. The mold was releasing a juice that killed them. That juice was penicillin. It was the first antibiotic. It changed the world. Before antibiotics, A simple scratch from a rose thorn could get infected and kill you. Strep throat was a fatal disease. Antibiotics turned terrifying killers into minor inconveniences. But we have become complacent. We used antibiotics for everything. We fed them to cows to make them grow fatter. We took them for colds, which are viruses, so antibiotics don't even work on them. Evolution never sleeps. The bacteria are learning. They are evolving resistance. We are now seeing superbugs that cannot be killed by any medicine we have. We are in an arms race with nature, and nature is very good at adapting. This brings us to the delicate position we are in today. We are the smartest thing that has ever lived on Earth. We have figured out the age of the planet. We have smashed atoms. We have walked on the moon. But we are also incredibly fragile. We depend on a very specific set of conditions. We need the air to have 21% oxygen. We need the temperature to stay within a narrow range. We need the ozone layer to block the UV rays. We need the soil to grow food. For most of history, we were too small to hurt the planet. If a tribe of hunter-gatherers burned down a forest, it grew back. If they killed too many deer, they moved to the next valley. But now, there are 8 billion of us. We are not small anymore. We have become a geological force. We move more dirt than the rivers. We change the chemistry of the atmosphere. We are altering the very things that keep us alive. We discovered earlier in our story that the Earth has a natural thermostat. Carbon dioxide acts like a blanket. It keeps the heat in. Without it, the Earth would be a ball of ice. But if you add too much blankets, you start to sweat. By burning the fossilized remains of the Carboniferous forests, coal and oil, we are putting millions of years of trapped carbon back into the air all at once. We are turning up the thermostat. The last time the carbon levels were this high, the sea levels were 60 feet higher than they are today. If that happens again, most of the world's great cities, New York, London, Tokyo, Shanghai, will be underwater. The Earth, of course, will be fine. It has been hot before. It has been cold before. It has survived asteroid impacts and supervolcanoes. Life is tough. Bacteria will adapt. The cockroaches will do just fine. The question is not whether life will survive. The question is whether we will survive. We are the only species that has ever had the power to destroy itself. But we are also the only species that has the power to save itself. We are the only creatures that can look at the stars and understand what they are. We are the universe's way of thinking about itself. It would be a shame to waste that. As we look toward the future, we have to remember where we came from. We are made of stardust. We are shaped by evolution. We are cousins to the worm and the bacteria. We are a brief spark of consciousness in a vast, dark universe. We have learned so much in our short time here. We have mapped the cosmos and the ocean floor. We have cured diseases and split the atom. But the biggest challenge is still ahead of us. We have to learn how to live on this planet without breaking it. And now, we must return to that lonely comet we left drifting in the dark back in part 3. Remember the visitor from the Oort cloud? We watched it get nudged by a passing star and begin its long, slow fall toward the sun. It traveled for millions of years, picking up speed, falling faster and faster as the gravity of the inner solar system pulled it in. It whizzed past Pluto, which was just a speck, past the gas giants, and crossed the orbit of Mars. It was screaming through the sky now, a mountain of rock and ice moving at hypersonic speed. It slammed into the Earth about 74 million years ago, and it hit, as promised, in Manson, Iowa. If you go to Manson today, you will not see a giant hole in the ground. You will see flat cornfields and soybeans. You will see a nice little town with a water tower. There is no jagged rim of mountains, no smoking pit. For a very long time, nobody knew the crater was there. It was completely hidden. The reason it is invisible is that the ice ages, which came much later, acted like a giant eraser. The massive glaciers slid over Iowa, grinding down the landscape and filling the hole with dirt and glacial debris, called till. They buried the scar under 100 feet of smooth soil. It wasn't until 1912 that a man drilling a water well noticed something odd. Instead of pulling up the normal sedimentary rock you find in Iowa, he pulled up deformed melted rock. It looked like rock that had been through a blender. Years later, geologists realized what had happened. There is a crater beneath the town of Manson that is 24 miles wide. If you could strip away the topsoil, you would see a scene of absolute devastation. The stone floor of Iowa was shattered by a blow so powerful that it momentarily liquefied the ground. This brings us back to a recurring theme in our story. The world is very good at hiding things from us. We missed Pluto's moon for decades because it was hidden in the glare. We missed the atom's nucleus because it was hidden in empty space. We missed the movement of the continents because it happens too slowly to see. And we walk right over giant impact craters because the Earth heals itself. The Earth is constantly recycling its surface. Rain washes away mountains. Volcanoes cover old land with new lava. Plants grow over the ruins. The Earth is a self-cleaning machine. This is why we have such a hard time finding the early history of our planet. The first billion years of Earth's history have been erased. The rocks from that time have been melted down and made into new rocks. It is like trying to read a book where the first 100 pages have been torn out and burned. But sometimes, the hidden things are not just history. Sometimes, they are threats. If you travel west from Iowa, you will eventually reach Yellowstone National Park in Wyoming. It is one of the most beautiful places on Earth. It has geysers, hot springs, bears, and bison. Millions of tourists drive their cars through it every summer. Most of them don't realize that they are driving inside the throat of a monster. Yellowstone is a volcano. But it doesn't look like a volcano. When we think of volcanoes, we think of a cone shape, like Mount Fuji or Mount St. Helens. We look for a peak with smoke coming out of the top. Yellowstone is different. It is a supervolcano. It doesn't build a cone. It creates a caldera. A caldera is what happens when a volcano explodes so violently that the ground collapses into the empty magma chamber below. It creates a giant sunken bowl. The Yellowstone caldera is huge. It is about 45 miles across. It is so big that you can't see it from the ground. You can only really see the shape of it from space. The entire central part of the park, the forests, the lakes, the roads, is just the floor of the volcano. Beneath the park, there is a reservoir of hot magma. It is alive. That is why the geysers erupt. The water is touching the hot rocks below. Yellowstone bursts every 600,000 years or so. The last eruption was 630,000 years ago. If Yellowstone were to erupt today, it would not be like a normal volcano. It would be a catastrophe. It would bury the western United States in ash. It would blot out the sun for years, causing a volcanic winter that would destroy agriculture around the world. But don't panic. Dew, in geological terms, is very vague. It could happen next Tuesday, or it could happen in 10,000 years. The Earth operates on a timescale that is indifferent to our schedules. This indifference is something we have to accept. The universe does not care if we are here. The asteroid that killed the dinosaurs didn't hate them. It was just a rock following the laws of physics. The ice ages didn't want to freeze the mammoths. It was just a wobble in the Earth's orbit. We are small, squishy, biological accidents living on a violent rock in a dangerous neighborhood. And yet, look at what we have done. In our brief moment in the sun, we have managed to figure it all out. We are the only species that has ever woken up and asked, "Where are we?" Think about the chain of events that had to go right for you to be sitting here. First, the universe had to be created with exactly the right laws of physics. If gravity was a little bit stronger, the universe would have collapsed instantly. If it was a little bit weaker, stars would never have formed. Then a star had to die. A massive, ancient star had to explode in a supernova to create the heavy elements, the carbon, the iron, the oxygen that make up your body. You are literally made of dead stars. Then, our solar system had to form in a quiet suburb of the galaxy, far away from dangerous black holes. Then, the Earth had to stabilize. It had to get hit by a Mars-sized object to create the Moon. The Moon is important because it stabilizes the Earth's wobble. Without the Moon, the Earth would tilt wildly and the climate would go crazy. We would have seasons where the temperature dropped to minus 100 degrees or rose to boiling. The Moon keeps us steady. Then, life had to start. As we discussed, this is a statistical miracle. Then, that life had to survive 5 mass extinctions. Your ancestors had to survive the Great Dying, the asteroid impact, the ice ages, and the plagues. There is an unbroken line of survivors stretching back 3.8 billion years. Every single one of your ancestors lived long enough to have a baby. Not one of them was eaten before they could reproduce. Not one of them fell off a cliff or died of a fever too young. You are the winner of a billion-year lottery. So, what is the point of it all? Science cannot answer that. Science tells us the how, but it cannot tell us the why. It can tell us how the atom is built, but it cannot tell us how to use that power wisely. It can tell us how the brain works, but it cannot tell us what a thought means. But science does give us a perspective that is almost spiritual. It tells us that we are connected. We are not separate from the universe. We are part of it. The atoms in your hand are the same as the atoms in the rock, the bird, and the star. We are all just energy and matter, dancing in different forms. We are also connected to each other. We are all cousins. Every human being on Earth is related. We all share the same African grandmother. We all share the DNA of the same ancient fish. And we are the caretakers of the only known life in the universe. As far as we know, we are alone. We have looked at the planets, and they are dead. We have listened for radio signals from the stars, and we have heard only silence. There may be life elsewhere, the math says there should be, but we haven't found it yet. For all practical purposes, Earth is a lonely lifeboat in a vast, dark ocean. This makes our life here incredibly precious. If we destroy this world, there is nowhere else to go. There is no planet B. We cannot pack our bags and move to Mars. Mars is a freezing, radioactive desert. We cannot move to Venus. Venus is a pressure cooker. Venus is a pressure cooker. We are stuck here, and we are stuck here together. The story of science is the story of us growing up. When we were children, we thought we were the center of everything. We thought the sun revolved around the earth. We thought the stars were just lights painted on a ceiling for our amusement. We thought we were made of magic, separate from the animals. As we grew up, we learned the truth. We learned that we are on a small rock orbiting a normal star. We learned that we are animals. We learned that we are small. This can be scary. It can make you feel insignificant, but there is another way to look at it. We may be small, but we are mighty. We have minds that can encompass the whole universe. We can sit in a chair in a room and travel in our minds to the edge of the Big Bang. We can see into the heart of an atom. We can compose symphonies and write poems. We are the universe's way of knowing itself. Without us, or beings like us, the universe would be just a lot of dumb rocks floating in the dark. It wouldn't know it was beautiful. It wouldn't know it existed. We provide the meaning. So, the next time you go outside at night, look up. Don't just look at the moon. Look past it. Look at the darkness. Remember that the darkness is not empty. It is full of faint, fuzzy worlds like Pluto. It is full of comets drifting in the cold. It is full of stars that are burning engines of nuclear fire. Remember the distances. Remember that the light hitting your eye left those stars years ago. You are looking into the past. Remember that you are standing on a spinning ball of iron and rock, covered in a thin skin of water and air. Remember that beneath your feet the plates are moving and the magma is churning. And remember that you are a collection of 7 sextillion, 0.00000 atoms. That's 7 octillion, organized by a complex code, capable of love and wonder. It is a very strange place, this universe. It is violent, huge, and mostly empty. It doesn't care about us, but it is also home. And for a brief, shining moment, We get to be here. We get to look at it. We get to figure it out. That is the greatest privilege imaginable. The astronomers in Part 1 were looking for flares on the moon and wobbles in the stars. They were looking for something out there. But the most amazing thing they found was not a quasar or a black hole. The most amazing thing they found was the realization of where we fit in. We fit right here, on this pale blue dot. So, take care of it. It's the only one we have.